Okay, welcome. We're broadcasting live from Santa Barbara, and we are here. Yeah, we're good. Okay, so welcome and good morning. We are broadcasting live from the basement of Winter Hall, room 110, affectionately called room 6 if you read it as binary. We are in CS-030, brand new opening graphics. Very excited about that. And this is our Mayterm seminar. We're part of a 5-week class. Today is exactly halfway through. I don't know if anyone is paying attention, but whoop. And today's lecture is scheduled for 2 hours. We're communicating via Slack for those who are on our Slack channel at #broadcastquestions. And we got a studio audience here as well, so hooray for our studio audience. And I think we're ready to go. Let's get into it. Make sure all of our notifications are off, and I always got to turn mine off. Been assaulted with phone calls recently, with just commercial stuff. I don't know. My number must have just gotten sold somewhere, but good to just arrive for a second. And so we have been opening our class thinking about various kinds of ethical issues, and we've been thinking about regulation. We started talking about legal regulations and the ways in which they are sometimes behind our technical regulation. We also introduced the idea of social norms as a way that regulation of our behavior happens, just expectations. We talked a little bit about economic regulation, the way that market forces cause us to change our behavior in different ways. And all those different forms of regulation are sometimes less than maybe what we should aspire to. Sometimes they're stricter than what we need to aspire to. And sometimes they allow things that we really shouldn't take on. The fourth thing that I want to introduce as a method for regulating behavior is one that's near and dear to our heart, and that's actually code. Code itself is increasingly becoming a mechanism by which we regulate behavior. And now this is a little different because in the beginning we were talking about legal regulations and the way that code might actually allow us to get around legal restrictions or give us access to things that haven't yet been legislated that maybe we shouldn't do. But what I'm talking about now is something slightly different. I'm talking about the way in which, because of the pervasiveness of software in our lives, increasingly the programmers are the ones that are dictating what can and can't be done in our lives. If you think about that for a minute, that's a little daunting. That means that programmers have a remarkable amount of power over what society looks like and how society is shaped and how our interactions happen. And so there are a lot of different things we can look at, but why don't we just start today by thinking about our favorite, social media. When we think about our behavior with one another, and we think about the fact that a lot of our communication is mediated by software, meaning that there is software that comes between us and our connections with other people, we think about that in the context of maybe we could start with text messaging. The people that write the systems that implement text messaging or messaging apps in general have dictated a lot of the ways in which we can communicate with one another. So for example, the introduction of group messaging enabled us to now have this conversation that was a multi-person at once conversation. Before group messaging was present, every communication had to be one-to-one. And so software fundamentally enabled us to change the way we interacted with each other at a distance. What other mechanisms are present in social media that cause us to force to interact with each other in a particular way? Well, that is a social media. What behavior does Instagram regulate? Or how does it change your behavior? The way you look. Oh, that's interesting. So you mean the way that you present yourself, right? Like, so Instagram has this reputation of being kind of a curated life. You only put archival photos on Instagram, and so therefore people always look their best. Is that kind of what you're referring to? So there's sort of, I know that there's sort of this funny, if you're ever out in public and you see a group of people around and you see them taking selfies, there's this really kind of funny behavior where they'll hold up their phone to take selfies and everyone will kind of, get like this. And then as soon as they're done taking the photo, they're like, they totally like change their countenance and their interactions with each other totally flip because they're no longer taking the picture for the curated life. Snapchat's a little different, right? My understanding is most of the time the way I mean, I know my experience at Snapchat, but most people interact in Snapchat. It's much more ephemeral. It's not archival, and so you don't have quite as much of that tendency to do the selfie pose. Is that fair? Do you guys experience that? Snapchat. It's casual, right? But that would take work. It doesn't get, by default that doesn't happen. So you still have to be careful what you send. But the nature of the medium, the way the programmers wrote Snapchat, cause you to exhibit different behavior, right? By virtue of the fact that those photos aren't kept around, you get all kinds of different behavior, from just sort of like goofing off in the camera to maybe more illicit sexting kind of stuff, or just, you tend to send more messages because it just doesn't have to be quite as formal as a result. That's all just because of the way the program's written, right? And so that code, your behavior is being regulated by some programmers somewhere, a group of programmers to be sure, not just acting by themselves, working with business interests and all kinds of stuff, but fundamentally it's just different code that's doing that. When we start thinking about that, that's pretty amazing. Lisa, you also mentioned last class about the way in which you had this conversation with people about whether or not they should take photos of you and post them online. And the fact that you have to have that conversation is a requirement of the way that the code is written. Because the code allows people to post photos of you, you now have a different kind of behavior that you must enact in actual space as a result. And were you like, outraged, I'm all about that? Or were you like, case study? Yeah. So fortunately, it's not usually if people are actually friends, they don't post highly embarrassing stuff about you, unless you're a certain kind of friend, and that's all they post about you. But so we'll think a little bit more about this. But these 4 ideas, the idea that we're regulated by law, economic forces, social norms, and code, this is an idea that comes from Lawrence Lessig. I want to be fair and give credit where credit is due, but it's very powerful thought as we continue to think about what it is that we're building. And of course, we're down in the weeds. We're not thinking big picture yet, but it's not a big step from where we are now to implementing Snapchat. Okay, administratively, we got a lot of stuff due today. We're in a heavy week. We're halfway through. Quiz on 6 and 15 due today. I saw some people turned in 6 yesterday. Got a programming assignment on Chapter 6 today, making a pyramid in JMonkey Engine. And we have an exam on Friday. For those remote participants, I'm asking you guys to do it through Proctor Free. And in Canvas, there's a test exam to make sure it's like 3 trivial multiple choice questions that are just to make sure that Proctor Free works. I'm a little nervous because no one has done that yet. And if we have some kind of problem with the technology, we're going to be in a bit of a bind. So make sure if you're in remote, you do that as soon as possible. It's pretty easy, but it'll just make sure that our mechanism is going to work. We got a programming assignment due the following Sunday and a quiz on Monday. Fortunately, though, to give you a little bit of space, we have no class on Monday because Monday is Memorial Day. All right. Questions administratively before we go on? Anything to tackle? Okay. So last time, we spent a lot of time looking at the different components of the Java collections framework. The hierarchy, collections, array lists, linked lists, stacks, hash maps, tree maps, maps, sets, queues, different interfaces, and different implementations. And we looked at all of them from the perspective of an application programmer, meaning from the perspective of someone that is going to write code that uses these classes. And you pick one out based on what kind of properties of your data you want to capture and you want to use. And so we know that a list and a set are different than a map, and we know some of the ways in which they differ. And so that helps us guide our framework about what we might eventually choose when we want to use these classes. But before we think too much about using those classes, I want to take a lecture, or 2 lectures actually, as we go through Chapter 16 of our text and look at how we go about implementing these classes. We've done one exercise in implementing where we implemented the clicker class. That was sort of introducing the idea of application programming versus systems programming and the design process. It was also a fairly simple class to implement. But even in that simple class, we saw the way in which you could have different implementations of a clicker, one that kept track of the number of times the clicker was clicked with an integer, and another that kept track of the number of times the clicker was clicked with a string that grew. We saw that we could have two different implementations, but the interface would be the same, so an application programmer would never know that there was any difference in the way that things were being implemented, unless perhaps they were timing efficiency or something. So today what I want to do is I want to implement some data structures to just drive home this, first of all, to drive home the difference between application programming versus systems programming. Or if you want to say it another way, using a class versus creating a class. Today we're going to be creating a class. We're going to create an array list and a linked list. We're not going to create it with all the features that the Java collection framework has, but just a subset of them. And in addition to this, it's going to help us to understand why there's different operations on these implementations, even though they're the same operation, might have different efficiencies as a result of choosing an implementation. Okay? So that's our goal for today. So let's get started by doing the design task and thinking through the list interface. Give me some feedback about what a list does. Like, how does it represent data? Like a shopping list, which means you have
a list. You just have like a normal items, and each one has a set spot.
Okay.
You can go to that spot and get it from.
Okay, so you have an ordering of items. You use the example of a shopping list. That's pretty good because things are at the top or things are at the bottom. It also has the property that you can have repeats. So in principle, you can put eggs at the top and eggs at the bottom. That'd be a little strange, but there's nothing preventing you from doing that in a list, but maybe not a grocery list. Okay, so if that's what we're going to implement, something that keeps track of things in order like that, what are the different methods that we are going to implement? What should we implement today? What should our list class do?
Add things anywhere.
Okay, I'm just going to put a little note so we can sort of remember it. So we want to add things. We want to add things to an arbitrary location.
Wherever we want, right?
You tell me?
Yeah.
Yep, okay. So we'll add something to a point in the middle, kindergartner handwriting. What else do we want?
Remove from I.
Okay, that sort of makes sense as well. What else? We could do clear. Okay, fair enough. It's a good idea. So like a size.
Yeah, you can have it. Tell you what types of elements are in it.
Okay.
Like what type of list is.
So I'm gonna hold off on doing types for another lecture. So today, why don't we just decide what it is we want our list to keep track of? Because allowing for different types requires a little bit more technological machinery, which we haven't introduced yet. So what should we keep track of on our list? It's shopping list, strings, maybe. Okay, so we'll keep track of strings. So add, remove, clear, size. This is more like a design exercise. So let's say we were keeping track of a shopping list. And just imagine, okay, we want to add something. Put that in there with an add. We could, what if we do add without any index? Do we want to support that? So just sort of throw something on the beginning or the end. We want to decide what the. Yeah, you could just do add 0. It's just a choice. Okay, this is a pretty good set of starting points. So let's go into Eclipse. I'm going to share a project with you. And what we're going to do is we're going to declare an interface for these methods. So we're going to say, what is it that lists must implement? And then we're going to do an implementation of array lists and linked lists that are going to do that. So add, remove, clear, size. We have our kindergarten handwriting there. And look behind the curtain at the magic software for a moment. Okay, great. So I've got a project set up here. I am not online yet. Let me connect on Saros. Dings, please. Wait for it. Not yet. Okay. Things will come. Too loud for sure. And we're sharing Project 13 basic data structures. There we are. That was what I was waiting for. And let's share that project. Why is it not allowing me to share a project? I do not know. Maybe because there's nothing in it? No, it shouldn't. Am I online? It looks like I'm online here, right? Oh, maybe yeah, Joy's the only one that gets to share it. Maybe it's just the case that no one was online yet. Let's just see. Great. Joy, you're like preferentially tagged. The system has identified you as a power user. All right. We're gonna go through the design process, and what we're gonna do is we're gonna design the interface, and then I'm gonna ask you guys to write tests. So we do test-driven development before we do the implementation. So for the time being, I'm gonna leave it so you guys can edit things. So just be careful because you can edit stuff, and if you do, it's gonna mess everything up. That's right. Okay, so now we're gonna start by creating a new interface. Sorry, I did it in the wrong spot here, and we will do a new interface. An interface is just a description of what methods must be implemented by particular classes. And we'll call this our list interface. And just so we differentiate it from the list interface that's present in Java, let's say we'll call it our list. And it's going to be public. And we'll put it in a package, edu.westmont.cs30. All right, so there's our interface. Is that sharing well with you guys? Show up? Okay. All right, so this is like a class, but we just don't implement stuff. So we're going to go ahead and spec out what the various methods are that we want. So we said we want to add something at a particular position. When we add something, we know that one thing that's going to happen when we add something to our list is there's going to be a side effect. The element will be stored in our list. So we not only need to specify a position, but we actually need to specify the data that we want to store as well, right? Because if we're adding something, how are we going to communicate what data we want to store? Right? So in addition to the position, which we'll call where, we also need to pass the thing that we want to share, and we'll call that what. Should our add method return anything? Doesn't seem like there's a necessity to return anything. So let's just start. We can change it if we want. We'll make it public, and it'll be void. And so there's a stub for our first method. Okay. And our second one we said is we wanted remove. So remove is just going to take a position and remove it. We don't need a what for remove. What should remove return? Anything? Doesn't have to. We could return the thing that we took out. Like if we remove something, we could return it. So remove the thing at 0, return the thing at 0. Why don't we do that? That'll make testing a little easier, actually. All right, we also said size. Size doesn't have a lot of complexity. It doesn't take anything and it returns an integer. And then we had a clear. Should clear return anything? That would be a side effect. I think no. Say no. Okay, now let's go through and let's just add some JavaDoc to it so we know what we're talking about. So this is an interface for an abstract list type. You want something to print it? Okay. Well, we don't need to say print list because it is in list. All right, let's say this will add a new element to our list at a specific position, and we should say that the first position is 0. Just be clear. The index of the element to add. Oh, and so when we add an element to that position, should it replace what's there, or should it just sort of insert it and bump everything else down? Okay, so we should clarify that. This will add a new element to our list at the specific position, moving everything else to the right, I guess. The right is a little weird because what's the right? Okay. The index of the element to add and the data to add. That's a little maybe not written the best way, but good enough. All right, remove. This will remove an element from our list, the element at position where, and return the removed element. Okay. All right, size. Oh, that was okay. Turn the number of elements currently in the list. Okay, and this will remove all elements from the list. No questions, nothing else. This will print out the contents of the list to the console. How should we do each element on its own line? All right, great. So we have an interface now. Anything else come up as we're going through there? Does it seem like we should add anything else to our public interface?
If we have duplicate elements, then we make it so it somehow says that.
So when we added something, if we wanted to add a duplicate element, how would that work?
Say we wanted like 2x instead of 1x. Like it would be like in the list when you print it out, it would be like 2x, x, something like that.
Well, let's see. Why don't we handle that for the time being just by having the string that we put in be different or include 2x. Okay, so that seems pretty good. And now we have enough information that we should be able to create two classes, and we should be able to write tests for them. So what I would like to do is I would like to let you guys loose to write some tests. So let me start by giving you a stubbed out class here. And let's see. We're going to need to make two classes eventually. But for the time being, we'll do linked list first. So let me make a linked list class so that you have something to instantiate. It's going to be public. It is going to include the interface for our list. Okay, great. The linked list does not need a main. Constructors from the class, we're good. Inherited. Okay. So now linked list is here with all of the interface elements implemented, but just stubbed out. And I will do the same thing now with the array list. Add the interface for our list. And that should be good. So now we have two things there. And so I'm going to task each of you with testing one of these methods in a test-driven development standpoint. So let's see, how about we have size, we have clear, we have remove, we have add. Oh, you know what we don't have a get, right? So we can add something, we can remove something, but we don't have anything where we can just get an element. So we need that. Let's go add that in here. So it's kind of like remove, but this will get an element from our list, the element of position where, and then that's it. Just the same as remove, it just doesn't remove it. All right, so I saved and updated our interface, and now you can see that these two now have errors because I don't have get implemented. So I'm going to ask Eclipse to go ahead and stub that out for me, and you can see it added get down at the bottom. And Eclipse, please add that for me. Get is now stubbed out at the bottom. We'll save all that. All right, so back to the point, having you guys write tests. So what I'll do is I will create a separate test class for each of you, and then have each of you be responsible for testing one of these methods. So let's see, can I, anyone want to take on add? Or I can just give it to you. All right, Boaz, you test add. Tim, can you test remove? Okay, Lisa, can you do size? And Joy, can you do get? All right, so now let me make some test classes for you to work in so we don't trample all over each other. So this is a new JUnit test class. The name is going to be our list test. Joy, what are you doing? Get. So I'll just say test get Joy, and that should be good. And you're going to do get. So I'll just do a good spot there. Okay, so you can go ahead and work on that one. And then Lisa, what did I ask for you to do? Size. All right, Tim, what are you doing? Move. Remove Tim once and for all. Okay, and then lastly, all right, so which one didn't we do here? We didn't do clear, right? So let me do clear for you just as a setup so we know where we're going here. All right, so my thing is I have to make sure that I've tested clear. So what I need to do is I need to create a list, add some things to it, and then call clear, and then check to make sure that clear was effective. So I'm going to do that by, and what we're testing first of all is we're just going to test linked list. All right, so we know that our interface is our list, so that's the type. The thing I'm going to create is going to have the variable name list. We're going to implement it with array list. And we just have to make sure that when we do this, we get the right one, because we don't want to get the official one. We want to get our class. And that looks OK. If I hover over it, you can see I get the right class there. All right, so now I'm going to say list.add add to position 0. What am I going to add? Well, I will add eggs, since we were in a shopping list mode. And now I will add to position 0 again. Butter, I guess. Then we'll make a cake. And we'll add flour, and we'll add sugar. What else goes in a cake? Milk. Anything else? Vanilla, I guess. Any other kind of cake. All right, so I should have 1, 2, 3, 4, 5, 6. So I'm going to assert equals that expected value is 6, and list.size better have 6 elements in it. Now this looks like I'm testing size, but actually I have to do that because I have to make sure that my condition before I clear is something that's going to change. So then I'm going to test 0 on the way. I need to import assert equal. Is it equal? Did I just do that wrong? No. Assert equals. Why is it not helping me out here? Help me out. I need to import that particular test, and I'm not sure why assert equals isn't showing up. Let's see. It's test. All All right, well, sometimes I have trouble figuring out what's going on with equals. So what I'm going to do is instead do assert true. That seems to work a little bit better. I'll just set this equal to 6. There we go. Okay, there we are. So now if I run this, it's going to fail because I don't have an implementation for ArrayList that works, but I can do that if I wanted to. I'm doing coverage so we can see what gets run. And you can see that just failed. And it failed where? Right here, because as soon as I tried to check the size, I got garbage back, and that didn't pass. So our point here is to write tests for the behavior that we expect, and then we're going to go back and do the implementation, and the test should pass as a result. All right, so that means that we're going to take some time to do that. I think it's probably going to take about 10 minutes to write each of you to write the tests in your own class. That'll take us to, let's see, 11:05. And at 11:05, we'll come back. We'll just review each of your tests and see if it looks solid. And then we'll go ahead and work on the implementation of a linked list. Sound good? Okay, so we are going to do that, and we're ready to go. Okay, we're back online, and what we just did is we went through and each individual wrote their own tests for testing different features of a class that doesn't exist yet. So Boaz was responsible for doing an add method, and so what he did was created a method that created an instantiation of array class, checked to make sure the size was what it should be with nothing in it, added something to the first position, then checked to make sure it was 1, then continue adding the same egg all the way down to position 12 and making sure that we have a dozen eggs in our list. Nice add. This is good because it's testing that we can put multiple of the same items in our list, which is one of the things that we expect to be able to do with a list class. And if we do coverage, we should see that it fails miserably because we haven't implemented anything, but it should compile okay, and it does. So we at least try the first one before everything fails. Okay, and then I did clear, and next we take a look at Joy. Joy was responsible for testing get, and so she created a list, added 1, 2, 3, 4, 5 different things, checked to see what, made a call to get right here, which will return the 0th element. It won't do anything with the 0th element, but it's no harm, no foul. And then on 19, we're actually going to get the same thing and make sure that it is equal to coffee. The only thing I would do here is because coffee is a object, I would use the equals here in order to make sure that we do what we expect. Okay, and I'm just going to copy that out, comment that out just to be clear that that's not strictly necessary. Good. Okay, then we look at Tim. Tim started looking at remove, and in the process of going through this, we realized that we had underspecified our class. So what he did is here, I'm going to change this so we get rid of the color coding. He created an array list and added eggs to it, and then checked to make sure that the first element was eggs. So that's good. His job was to test remove, though, and so after asserting that the list was in a state that he understood, he removed the first element and then wanted to check to make sure that the element was removed by checking to make sure that there was no element at position 0. But we hadn't specified what happens if you try and get something from a list that has no elements in it. And so offline, what we decided we would do so that we would match what happens in the books example is that we would throw a no such element exception. And so instead of testing that what we returned was either equal to nothing or null, what we're going to do is check to make sure that when we call get 0, we throw an exception, and we're looking for this particular exception along the way. So this right here is a closure. This is an example of a small function that's written in line. This is a function that takes no parameters and it returns nothing and then runs this code in the process. So what we're doing here is we're passing a function as a parameter. That's sometimes called a closure or a lambda, a couple different names. So then just to make sure the world works as we expect it to be, he added bacon to our empty list, made sure that the list was as we expected it to be, and then did the same check. So what I'm going to recommend here is that we actually add 2 elements so that we test a different case. So because otherwise we'd be testing the same code as the previous one. So now we're going to add bacon. We'll add orange juice. We'll check to make sure that check to make sure that position 1 is bacon now because orange juice is going to bump bacon over. We'll remove 0. That should be the orange juice we get rid of. And now we're going to check to make sure that get 0 is orange juice. Orange juice. Okay. And need to import that. Oh, sorry. Search true. All right, that seem okay? Now, only by virtue of the fact that we have instantiated this or implemented our list with an array list does this make any difference about which class we're using. And in fact, we said that we were going to start by implementing a linked list, and then I gave you examples of array lists. So I'm going to go back, and I'm just going to change all this to linked list. And it shouldn't matter. Oh, wait, we didn't do Lisa's. Did we do yours? Okay, let's do Lisa's. So Lisa was checking size, and she added a bunch of fruit to a list, 1, 2, 3, 4, 5, 6, 7, and then checked to make sure that the size was 7. So that looks good too. we're going to go through and change all these to linked lists. And you can see that we can just do that because the only features that we were exercising were features that were associated with the OurList interface. And so as a result, we could use either of our proposed implementations in order to test the correctness of our code. And so that works there. Great. Okay, well, one other thing that was important about our class is that we also needed a list iterator. We needed to be able to iterate over our items. We could do that with an index-based iteration, but we know that in some implementations, a list iterator can be more efficient. So we also need to do an interface for a list iterator. So what sort of things should we have a list iterator be able to support? Okay, so forwards would be next. Forward would be next. Previous would be previous. Has next and has previous would be important to be able to check those. And then typically with a list iterator, you want to add an element, remove an element, and reset the element as well. All right, so I will just quickly do these. And I will create a new interface. Here we go. And this interface, we'll call it our list iterator. Boom. Great. And what we're going to have here is we will have a public returns true or false if it has a next. And just for the interest of time, I think we'll just implement a next. So the iterator only goes forward and won't go backwards. So next, of course, moves you is like a cursor. So it's going to move you over the next element and return the data that you walked over. And then we needed an add, and that we need the thing that we're going to add. We don't need a position for an iterator because when we add something, the iterator is at a particular cursor position, and so we already know the location to do that. And same with remove. But in this case, we will return the removed element. And then the last thing we'll do is we will have a set, and set will change the data that we're currently in front of, and we will return the data that was removed. So it's like a replacement. Okay? We can write a test for that after the fact. If we were doing test-driven development properly, we should go ahead and, well, all right, let's do it properly. Let's do a list iterator test. I'll do it so we can run through it quickly. So JUnit test case, we have an rlist iterator test, and great. And we'll check. I'm just going to write one test that has all of it, but I'm going to just click that one so that it gives us a place to work from. All right, and I'm going to go and let's see, Lisa, you had a nice setup for your list. So we'll go there. We'll go to our list iterator test. Okay, so this is just going to build out a list for starters. So to get the iterator, we're going to have to say list.getIterator. Well, that's not part of our interface yet. So actually, we need to go add that to our list interface as well. So in addition to all these, we'll add something at the bottom, which is public our list iterator get iterator. Okay, as soon as we added something to our interface, the two things that implemented our interface needed to be updated so that they have that method actually implemented. We stubbed it out at the bottom, not doing anything yet. Same thing with ArrayList. Add the implemented methods, unimplemented. There it is at the bottom. Save everything. Go back to our list iterator test. Okay, so now we're going to get a list iterator. Oops. We'll store it as an iterator, and it better be the case that because our iterator should start at the beginning, that iterator.hasNext better be equal to true, because we're starting at the beginning. And then we want to assert true that iterator.next better be equals to blackberries. Does that look right? And then after we've moved over one thing, we can then call iterator dot add, and we will add Lisa. Quick, I need another fruit. Is that a fruit?
Yes. It's a really smelly fruit.
Great, thanks, Boaz. Thanks for that. So now we're going to assert that our list changed correctly. So we want to assert that it is true that our list.get1, because our first one is blackberries, we stepped over it and we added durian after that. So get1 now better be equals to durian. All right, so that'll test our iterator add. So now let's just make sure that as we step over the next element, it's now blackberries, durian, papaya. Papaya. Now let's test that we can reset that data. I fear doing this, but Boaz, another fruit. Starfruit, or as I prefer, carambola. Now we've replaced papaya. That should be position 2. Make sure I spell them right both ways. All right, and then we have tested that we replaced papaya okay. And so now we're going to step over the next one, and the next one better be blueberries. And now we're going to remove the blueberries. Did I spell it wrong? Carambola. Starfruit is a lot better when you pick it off a tree. My grandmother had a starfruit tree in her front yard in Florida, and it tastes like a cross between an apple and maybe a grapefruit, kind of. It's got kind of a crunchy texture. It's got a waxy outer side. If you slice it lengthwise, it has a star cross section. It's a little bit sour, but if you get them from a tree, they're sweet. So it's good. All right, so we want to make sure that if we remove something at this point, that is going to be blueberries, because that's the element we just walked over. And then we want to make sure that the element that was where blueberries was, which should be 3, should be raspberries. All right, and now the cursor is, well, where is the cursor? Okay, let's start. We started with our iterator. We saw that it had next. We walked over blackberries, and we added durian. So durian is behind our cursor. Then we walked over papaya. Then we set papaya equal to carambola. So that's the second one. So we want to make sure, third one, because we added blackberries. So check that's true. Now we're going to step over blueberries. We're going to remove blueberries. So blueberries was 0, 1, 2, 3. And so now 3 is raspberries. And we just removed that, so we're before raspberries. So we should be able to say iterator. We should be able to check each of them here. Just step over from blueberries. We step over raspberries. And then after raspberries, we step over pineapple. And then after pineapple, we step over mangoes. After mangoes, we step over strawberries. And then at this point, our has next better be equal to false, because we've gotten to the end of our list. All right, so that should test everything on our iterator in one fell swoop. Okay, are we ready to implement it? Okay, what do you think's wrong? Just a feeling. Okay, well, we'll find out when we implement it. We'll have to debug it. Got a bad feeling. We all have bad feelings. Okay, so that's our list iterator. We did the design process by thinking through what a list should have, what a list iterator should have, and then stubbing out the interface, creating some stubbed out implementations, actually writing the tests before we did the implementation. And in the process of doing those tests, we realized we had an undefined behavior when we tried to get something from an empty list. So let's go ahead and implement it. The point of implementing it here is to make sure that you guys understand the abstraction. We're going to implement it with a private inner class called myNode. And my node is going to contain the data, and it's going to hold connections to neighbor nodes. So remember that a linked list is like people holding hands together. And that each time we create one of these nodes, it's like adding a person that has the data and the connections to its neighbors. Because we don't want application programmers knowing anything about about the way we implemented this, node is going to be a class, a private inner class. And that's something we haven't seen before, but we'll go ahead and implement it. Okay, so here we go. Make some space, go to our linked list. So the first thing we're going to do is we're going to add a class internally to our linked list. So it's going to be a private class called myNode. And each node is going to have the data that we're going to store, and that's going to be called string. And we're going to have a connection to another myNode data piece, another myNode. And that's going to be next. All right, so if you look at this, we're doing something a little bit crazy. We just defined a recursive reference within a class. We said the class is called myNode, but it actually contains a reference to myNode as well. All right? Because a given node has to hold hands to the element next to it. We'll make each of these elements public, which means that we can access them within this class, but because the class itself is private, no one else is going to be able to make a class for us. And then the linked list, we're going to keep track of a link, private link, because we don't want anyone who's using our linked list to know how this works. We're going to have the first element in our list, and we're going to keep track of that. That's going to launch our chain. So when we first start out constructing our list, this is going to be equal to null. We're going to assign it equal to null. Okay, which one should we tackle first? Add. Okay. So, what are some possible situations if we're going to add something? Well, the first thing is that we might have a null. We might not have anything in our list for starters. And so if first is null, then the only thing that we can add is something to position 0. Right? And since that's our initial case, that's our initial condition, that's something that's pretty easy to test. So we'll just say if first equals null, I guess we want to say and where equals 0, then we're in good shape because we're in the opening situation. And what we're going to do is we're going to create a new myNode class. We don't have a constructor up here. Let's make a constructor real quick. No, it's not making a constructor. We'll use the default constructor. Okay, so we'll say we're going to create a node to hold the data that we're adding. So there's a new node. That's going to be where we're going to put our data. And we're going to make the node.data equal what? And node.next, because there's nothing else in this chain, is going to be equal to null. So we're going to create a box, and we are going to put the data in it, and we have nowhere to send it. We have nowhere to send it next. The next one will be equal to null. And then the last thing we have to do is we have to change first so it equals the node that we just created. How do we feel about that? Need a visual to make sense of that? Okay. Let's see. Let me see. How can I do a visual? All right. I'm going to switch back to Keynote. I'm going to kick out of Keynote. I am going to go back to Keynote, and I'm just going to make an empty slide for us so that I can write on something. And then I'm going to play it, and I'm going to draw. All right, so what we just did is we have this linked list class here. And inside it, we have this variable first. And when we want to add something, we instantiated a new node here. We put the data here. We said the next node is pointing to nothing. And we said first is now pointing equal to this node. Eventually, we're going to add some more nodes over, that it connects to, but for the time being, those are blank. All right, so that's an initial condition. That's the condition where, that's the condition where first equals null and where it equals 0. Well, let's say that first is not null. Let's say, and I guess if that's the case, then we can just return from that point. All right, so now we need to walk down the list and find the position that we care about. And so in order to do that, we'll say if first equals null and where, I guess if we get past here and first still equals null, then we have a problem. And so we'll throw new no such element exception. We can't add an element to a spot that doesn't exist. Okay, so that makes sense? First is the first hand in our chain. There is no first hand in our chain, and you just tried to put something at position something other than 0, so there must be a problem with that. But if we know first is the first element in the chain, then we're going to walk down that chain until we get to our position we care about. All right, so we'll create a new my node called walker. And we'll set that equal to first. And we'll set a new integer called position, and we'll set that equal to 0. And we're going to keep walking down our chain until either we run out of nodes or until we get to the position we care about. Okay? And because we're going to add an element, we actually need to stop one before where we want. Let's see, one before we want to be at. Okay, so while walker is not equal to null and position is less than where minus 1, we want to walk down our chain. So we'll say walker equals walker.next and position plus plus. So we have a reference to a my node that's pointing at one element, and we're going to just move it down the chain one by one. So once we get past this point, if walker is equal to null, we ran out of space. We didn't get to a position where we could add something. So we'll add this here. If walker equals null, then can't add an element to a spot that doesn't exist. But if walker doesn't equal null, then we're pointing to the element right before where we want to add something. So then what we're going to do is we're going to create our new node. We'll say my node equals my node, just like before. We'll say the node.data equals what? And we say that the node.next is going to be equal to walker.next. Nope, that's not right. Sorry, walker.next. .next. And walker.next equals node. We're done. So this is Java, so we say new. Okay, so what just happened? Great question. we have a list like this. These are all the nodes. And each one of the next elements points to the element in the list as such. And then this one points to null. When we said add something, say, to position 3, let's say position 2, Walker starts out here, and position is equal to 0. That's not where we want to be. We want to be at the position where position equals 1. And so we say Walker equals Walker.next. Walker equals node.next. So now instead of pointing here, it points to what this points to. And now position equals 1. Now we're 1 before where we want this new element to go. So we want our new element to drop in there. So we're going to create a new node element. We're going to put our data in there. We're going to say, I might have done this wrong. So we want to say Walker.next. We want to say our node.next equals Walker.next. So following this arrow right here. And we want to say Walker.next equals this node. So we want to insert it right in there. I think that my code is not quite right. Let's go back. And now that's going to put it in position 2. 0, 1, 2. Great. All right, so it should be that node.next equals Walker.next, and Walker.next equals node. Good. Okay. That was probably a more complicated one to start with than we should have done. Let's try doing get. And then if we have get and we have Walker implemented, then we should be able to run one of our tests. Okay, so get, we know we want to walk down our chain to a particular position. And so we're going to create another Walker, and we'll say my node Walker equals first. And we'll say integer position equals 0. And again, we'll say while Walker not equal to null and position less than where, we'll say Walker equals Walker.next. We'll say position plus plus. If we get out of this and Walker equals null, then we walked off the end of the list before getting to the position that we wanted. So we're going to throw an exception there. If not, then Walker points at the thing we want, and so we'll return Walker.data. And got some kind of error. What's my error? Let's see, got an error. What's my error? Rename method get. Assign parameter to new field. Did I delete something I shouldn't have deleted? What does this one say? Duplicate method remove. Did I copy a whole bunch of stuff? Okay, there. Okay, so get. Let's take a look at that. We're going to start at the first node, and we're going to walk down. So what's happening there on line 71 is a really important thing to understand in terms of referencing, following through. Now, if we go over to Boaz's, or Joy and Boaz both had one. So Joy said, let's add coffee, let's add tea, let's add juice, let's add soda, let's add milk, and let's just get. So if everything worked okay, if we don't have a bug in our code, then this should clear. This should run okay. I don't actually know if it's going to work, but let's see. Oh, huzzah! It worked. Oh, I feel good. I wasn't sure that was going to happen. What's that? Your bad feeling was wasted. You didn't trust me. All right, so that's good. Get worked. We walked down our list, and that. Let's celebrate by taking a 5-minute break. Okay, so we will come back in 5 minutes. We have got it's 11:37, so we will come back at 11:42, and we will implement our next chunk of the linked list infrastructure. Okay. Question? Yeah.
I have a problem.
Yes, you have a problem.
Yeah, my YouTube link is not working for some reason. It's frozen. It's called, yeah, it's frozen on the slide. Check it out.
Do you have pause written? Yeah, I'll check it out in a second. First, let me go offline though, because whatever's about to happen, I don't. All right, so we're implementing linked list. And what we're trying to do is we're trying to demonstrate different ways of actually doing a linked list. And we successfully got our get and our add to work. So that's a win. Now what we want to do is we want to get, well, let's see, what's the next one that we haven't filled out yet? Why don't we do size? Size is a pretty straightforward one. It's very similar to what we just did with our Walker one. And the only way that we can, because a linked list is created by chaining together these nodes in sequence, there's no way to know how many things are in the chain without walking down and counting them along the way. All right, so that's exactly what we're going to do. So in the size method, first of all, we can just say if first equals null, then what's our size?
1. Oh, wait, 0. Well, 1.
0. If we do
first equals null, what about 0?
If first equals null, then we don't have anything in our chain, right?
I was thinking, yeah. I was thinking of 1.
So because it's not equal to null, we can now say that our walker is going to point to whatever first points to. And so we'll now be at the head of our chain. And we can create an integer that says position equals 1. And now we'll do the same thing, but it's a little simpler. While walker is not equal to null, we'll say walker equals, actually we want it off by 1 there, we want that to be 0. Walker equals walker dot next, and then position plus plus. So let's imagine that we have one element in our chain. Walker will point to that first element in our chain. Position will be equal to 0. Walker will not be equal to null, and we'll say walker equals walker dot next. If the walker just walked off the end of our chain because the last element in our node is null, then we'll add 1 to position, and we'll never do the loop again. So we'll end up with the answer 1. So that seems pretty good. So I think that's going to be all right. And so when it's done, we're going to want to return our position. So now we should be able to test our size. So who did size? Lisa did size. So we should be able to run this because we have add and size implemented, and that should work. Hooray, we got size working okay. All right, so let's go back to linked list. What do we have next to implement? Clear. Well, boy, that's easy. Anyone have any recommendations on how to write clear? Even faster. Well, no, because we want a linked list, but we just want to have no elements. Well, size is not something that we set. Size is something that we generate. We could do that. We could remove everything one by one, but there's actually a much faster way to do it. A virus. We have this first variable, which points to the first element in our chain. So if we want to get rid of everything, all we have to do is say first equals null. And now we've lost every reference to our chain. Yeah. Because without first, we have no way to access our chain of elements. And so now they just get disconnected from all references.
Are they still stored somewhere in memory?
Briefly, but now that there are no references to them, the Java garbage collector will go through and clean them up. Yeah. So that's kind of remarkably easy. And so if we have done that successfully, did we have someone do clear? I did clear. And I don't access anything else. Huzzah, we passed clear. All right, what's next? Print, we'll get back to that one. Get iterator, we'll get back to that one. And remove. Okay, remove is going to be a little bit hairier because what are we going to do with remove? Well, let's see if we can sketch this one out. All right, so clean that up. Done. Please go away. Please, all of you go away. Sorry. That's not what I meant. Okay, let's see. I can't. All right, I need to get another drawing space here. So let's do as much. And maybe if I just play it, clear it for me. Great. All right, so now remove, we're in the situation where we are looking at having a sequence of elements. First points to the first one, and each individual element has a link to the next element and its data. That points to null. And then we know we're going to want to remove something, like say we want to remove position, so this is 0, 1, 2. Let's say we want to remove position 2. So this is the one we want to remove. So what we're going to need to do is we're going to need to have a walker that goes here and then here and stops at the element one before the element that we want to remove. And we're going to need to adjust the element. First, we're going to have to make sure that the element is there. And then we need to adjust the element so that this, instead of pointing here, bypasses this element and points here. And now if we were to walk down the chain, we'd go here, 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 here. And this one is just going to exist out in memory. It'll get garbage collected because we've broken this link here. All right, so now let's go ahead and implement that. So we can start. I'm going to take some of the code from our add because some of this is useful. Not the piece that actually adds the data because we're actually removing elements. But we'll start and we'll say if first equals null at all, then we've got a problem because you just asked me to remove something that doesn't exist. So that's a problem. And I guess actually if first equals null or where is less than 0, that's a problem too. Probably could have added that to our previous ones. All right, but given that we actually have a chain and given that we're looking for a particular position, we're going to do our walking business here. We're going to say the walker is pointing to the first element in the chain. Our position equals 0. We're going to continue walking as long as we don't walk off the end of the chain. If we do, walker is going to equal to null. And as long as our position is one less than the element that we want to remove, because we're going to need to be before it in order to bypass it. And we're going to keep walking down there till we get to that position. If we end up walking off the end of the chain before we get to our position, then we'll say, oh, I guess we should say can't remove an element. So can't remove an element from a spot that doesn't exist. Put that here as well. All right, so now we're in a situation where walker is pointing to the element before the one that we want to remove, and we just need to make sure that there is an element present on the next step to actually remove. So we want to say if walker.next equals null, because the next one is the one that we want to remove, we'll throw an exception as well, because that one doesn't exist. We're stopping one before the one we want to remove. But if the next one isn't null, then all we have to do is say walker.next equals walker.next.next. We're done. I guess we want to actually save the data. The data that we want to return is walker.next.data. And we want to return that. So this is the key line. Line 59 is the key line. This is where we slice off the node in question. We bypass it by saying whatever walker points to, the next element shouldn't point to this one. It should point to what this one points to after that. So we're just bypassing exactly like we saw in the diagram. And so now we should be able to run Tim's remove code, and if everything works okay, we should get an exception in some cases, and we should get removal in the other cases. This is the one I'm nervous about. Let's see, because I'm not really super familiar with the Java 5 assert throws. Boom! Okay, it broke. Great. Great. It's a learning opportunity. It's a learning moment, teaching moment. When something doesn't go like you want it to go, take a moment and step back and debug. Easy enough. So we created a list, we added something to our list, and we tried to get the first element from our list, and it didn't equal the right thing. That is a problem with the test, because we should have been using equals, because it's an object. Now let's rerun it. Okay, so we got past the first element. So that was okay. Where did we actually crash here? Can't remove an element from a spot that doesn't exist. So when we tried to remove position 0, it didn't work. Oh, that's interesting. So that's a special case. We have to add a special case to that code, because if we look at our remove, what did we do? We said if first equals null, then we can't remove the first element. Okay, that's fine. We set our position equal to 0. If the first thing that we want to remove, if we want to remove position 0 and that's the only element, we need some special code for that, because our walker doesn't work. Our walker assumes that we've got 2 elements in our list, and we only have 1 element in our list. So we'll just special case that. We'll say if first not equal to null, and where equals 0, and first.next equals null. So this is a list with 1 element. So what is the situation here? We have 1 element in our list, and we're asking to remove position 0. So we just say first equals null, and we're done. We got to capture the data again. Because if we have 1 element in our list and we remove the first element, our list is empty. So if we go back to our test, let's see how that works. Okay, so far so good. We did a little bit better. We got all the way down to here where we tried to remove element number 1, and that's bacon. All right, let's go back. Let's make sure our equals method is how we're testing equality for objects. Try that again. All right, so something failed. List.get1 does not equal bacon. That's funny because we've already tested get. So why are we having this problem? List.add0 is we added bacon and then we added orange juice, and that should have bumped orange juice down. We should have gotten bacon, and we did not. Anyone see what the error is? Did I misspell bacon or anything? Okay, well, here's what we're going to do. We're going to put a breakpoint in here, and before we try and check what it's equal to, we're just going to look and see what the state of the world is at the moment before we run that test. So I'm going to debug this as a JUnit test. That's true, but we're just asking what what position 1 is equal to. Yeah, it should have bumped bacon down. So let's see what happens. So now we're stopped at line 23, and we can look to see what our data structure looked like. So here's our linked list. And if we open it up, we have our first node, and we can look at what our first node is. And the first node says bacon, but that's not right, because orange juice should have bumped bacon down. So I think what we just discovered is something is wrong with our add method in the case where we want to add something to the beginning of the list. Something's already present. But we can look at this and say, what's the next element? The next element is orange juice. So can you see how that structure is present here? Here's our list. Here's our first node. Here's the data. Our next one points to another node. It's orange juice. Is this violating what we thought? Because when we added bacon to to position 0, it should be bacon. And then we add orange juice to position 0. It should have bumped bacon down, right? Okay, so something's wrong with our add then. So let's stop our test. What's that? Yeah, well, so here's the thing. This is exactly why we do tests. This is why I love tests. Because if we hadn't had the tests and we thought we had done okay, and now we had taken this code and put it into some production environment, it would have been totally buggy. And we would have gotten, our production environment would have been messed up, and all of our library software would have been messed up. So I kind of like testing, even though it's like shows your problems. So let's walk through the situation when we're actually going to add something. So we're going to put a breakpoint 1 earlier, and we'll step through the code and see what happens. All right, so now we're in line 23. No, we're at line 22, I hope. Why didn't we break? Okay, let's try that again. Let's try that again. We had 2 versions of our code running. Try again. All right, we're at 22. There's a problem with reality. Okay, we're at 22. We have a list. We haven't run 22 yet, and we can see that the only element in our list is bacon. That's our data, and the next element points to null. Okay, so the world is as we think it is. So now we're going to step into our add method. We're going to hit the wrong button and step over it. Then we're going to stop it, and we're going to restart. You can't do that in Eclipse. You can do that in Visual Studio. Yeah, that's one of the things that I will grant that Visual Studio is better in that regard. All right, so let's step into list.add. We had to make an integer, so step into list.add. Here we go. All right, if first equals null and where equals 0. So that's not the case because first isn't equal to null. If first is equal to null, it's not. We're going to set walker equal to the first position and position equal to 0. So that's good. Now, is position less than where minus 1? Because it is not. It is greater than, right? Because position is actually 0, and where minus 1 is minus 1. So we're actually kind of in a good spot. So we're going to step over that. Walker's not equal to 0. Walker equals first. So we're going to create a new node. The data is going to be what? And we're putting it, yeah, this is just an error when you have the same thing that happened in our remove. We have an error in the logic when we have just one element in our list. So let's handle just one element in our list then. So if first is not equal to null, and where equals 0, then we're going to say create a new node. Node.data is next. Next.node equals first. And first equals node. We just have a special case for that particular case. Try running that again. I don't want to debug it. Stopping all the running processes. I'm going back to our JUnit test. Coming down here to, I want to see the coverage of test. Restart, there we go. Let's run that again. Hooray. And we successfully got Tim. So we successfully removed Tim. So our general case then is the way the walker and the position code worked is that it assumed that your list had two or more elements in it. And so we just had to be super careful for the case when we had no elements in our list and the case when we had one element in our list. And that's because anytime you wanted to do something, you always had to stop one element before the spot or the element that you wanted to add or remove. I think that's almost everything we implemented, I think. Is there anything else left we have to implement? Add, remove, size, clear, get. We haven't done the iterator yet, but I think that is everything that we've tested so far. So if I right-click on the package name, and I say coverage as a JUnit test, it should run all the tests that are present. And the list iterator test failed because we haven't done our list iterator yet. But everything else passed, and you can see we've got pretty good code coverage. We have some situations that we're not testing in our remove, but that's okay. We don't need to do everything. Okay, I feel a little bit like this is an endurance test in trying to implement the linked list, but we've got to do one more. We've got to do one more element. That's our get iterator. So we're gonna bash through it. Hopefully, we'll be able to finish the list iterator today, and then we'll be able to do the same thing with array list tomorrow. But that'll go a little bit quicker because we can use the exact same tests, and array list is a little bit easier to implement. All right, so here we go. We need, we're at speed coding. All right, code forge. All right, so we're going to return something from get iterator, and we need something that is of type our list iterator. That's the interface that we have declared. We're going to need to implement our own iterator within our class, and so just like we have this node class, we're actually going to create a private class my iterator, and that is going to implement all the methods of our list iterator. So we'll have this class that we're using internally to do iteration, and we will return it when necessary. So I just made the class. We can just implement it here. And then down here in our list iterator, when we want to get an iterator, we're going to have to create it. So let's go up to our iterator for starters. Let's create a constructor for it and say my iterator internally, our iterator is like a cursor. So we're going to keep track of the position before and after our current location. And when we start, that's going to be equal to null, and after is going to be equal to first. Actually, we don't need to do anything if that's the case. All right, so that means that our very first position, our iterator is going to exist between these two elements. So if you just recall for a moment, this private inner class, mylist iterator, that arrow represents the iterator. We're keeping track of the node before and after. So we don't want our application programmer to be able to see how we're implementing it, and so we're hiding the implementation behind this private class. Okay, so if something has next, then it's just whether or not after is null or not. So if after is not, hello? Okay, I'm not sure what just happened. My computer is still broadcasting. I'm still live, and the screen is black. Okay. Oh. Okay, that was super fun. Let's have the kids boo. Okay. Boo. All right, let's try that again. All right, so whether or not there's a next element is just whether or not if after is not equal to null, then there's a true. Then there's something left. So return true. Otherwise, we'll return false. Flas. Okay, for next, we're going to say that before is going to equal after. The thing that we return is going to be what we're about to step over, and after is going to equal after.next. So we're just going to move the cursor ahead a bit. We have a problem if after is null, so we will just say if after equals null, then we'll throw a no such element exception. All right, that's okay. So to add something to our iterator, what we're going to do is we're going to splice it in. Our add iterator is pointing to something before and something after, so we just need to break that link and drop in the new element. So add is just going to, we'll have a special case if the before was null. So if, this is if we're at the very beginning. So if before equals null, then let's make the node that we're going to put the data in. So my node equals new my node, and we'll say node.data equals the new data, and then we're going to have to set up node.next. So we'll say if before equals node, then we're going to put this in the beginning. So we say node.next equals first, and first equals node. Otherwise, and then we'll return. That's good. Otherwise, we know we're in the beginning somewhere, and we'll say before, let's see, we have to do this in the right order. Node.next equals before.next. That'll link in node, and then we say before.next equals node. That splices it in. And then if we want to remove something, then we need to make sure that our before is not equal to null. So if before equals null, remember the contract for remove is you remove the last thing you stepped over. So if before equals null, you didn't step over anything. So if before equals null, then we will throw the exception. Okay, otherwise, we'll say that we want to remove the thing before. So we'll say, we have to check to make sure we're at the very beginning. So if before we're not going to be able to do this. No, we're not going to be able to do it because we don't have access to the thing before. Yeah. We don't have the node beforehand, so we're going to have to do. Yeah, you could store before, and before. Well, we could do two things. We could either store two previous before references, or we could walk through the entire list and find the element one before we want the one we want. The first option is going to be cleaner, but take more care. Okay, we can pull it off. That's what we're doing. All right, so we're going to say my node walker equals first, while walker.next not equal to before. Say walker equals walker.next. All right, so let's just look at the case where we have a list with nothing in it. If we have a list with nothing in it, then we're already going to throw an exception. Let's say we have a list with one thing in it, and we're at the first. Our iterator is positioned between the first and second element. Then my node walker equals first will be the first element, and walker.next not equal to before. So we have to be a little bit careful. So if we say we need a special case if before equals first, then we're just removing the very first element, and that's easy enough because we can just say first equals before.next, and before equals null. So that removes the first element. Good. Then the general case, we're going to walk down the list until walker.next equals before, and then we will say walker.next equals before.next. And before equals walker. In each case, we need to make sure that we capture the data we want. Right? So string return equals first equals before.data. Turn ret. I'm going fast. I'm not sure I believe myself here. Okay, I think that will do it. Right, so in which case we should be able to run our list iterator test. Have we done everything? Oh, set. Set's easy. So we just say if before equals null, then we can't set it, so we just throw our exception. Otherwise, we say the data that we want to return is what is currently at before. And we say before.data equals data. And we return. Run this. error somewhere. Let's see where our error is. We created our iterator, and iterator.hasNext was not true. So we have a problem in hasNext. Let's go take a look at that. That seemed like it was easy. Why is this having a problem? Before equals null, after equals first. If after is not equal to null, oh, I suppose if there's nothing in the list, then you would, no, that's okay. There's no next. Okay, I don't understand what's happening that's making that go wrong. Oh, maybe did get iterator not return anything? Did we not implement that? Oh yeah, we didn't actually return an iterator. Changing the name so it matches the slides. There we go. All right, let's try running it again. Huzzah. Great. It passed. All right, so that's speed implementation. It's not I worry that what I just did, I did so fast that you guys aren't exactly following what's happening. And the code for doing a list, for doing linked lists is a really important thing to understand, because the manipulation of these iterators is a really common thing that needs to, the iterators and the references is a really common thing that happens. The one advantage is that the textbook walks through this, and the textbook implementation is slightly different, but it does show you a little bit more visually what's happening in each one of the different methods in terms of how those different references are being maneuvered around. But nonetheless, you guys, what I'll do is I'll put this code up on Canvas for those who are following along remotely. Everyone who's present here should be able to see the existing code as it's there, so you have an opportunity to step through it. And what is very valuable in this regard is to go back through and, as much as possible, to step through in the debugger and see if you can understand at each step what's happening to make this work. Being able to visualize it in your head and move those references around is a super critical skill. Okay, we are out of time. Any last questions or thoughts? A lot of stuff due today. Next lecture we're going to go through and we're going to do the same work, but we're going to do it with an array list instead. And again, hopefully it'll be a little bit faster. All right, and so with that, we are done for today. Thank you for your attention. We are out.